Hello everyone and welcome to this POP webinar. My name is Nick Dingle and today I'll be describing a case study of work the POP project undertook in conjunction with Zenotech to investigate the performance of their zCFD computational fluid dynamics package. As well as introducing some of the findings from the case study, I'll also be talking more broadly about the POP performance analysis methodology and giving you some guidance on how we went about gathering the performance data that we used in this study. Please feel free to ask any questions you might have as we go along. There'll be plenty of time to answer questions at the end. To ask a question, type them into the questions section of the GoToWebinar control panel. You might need to click the small triangle next to questions in order to open up first. Before we get into the actual case study itself, I'd like to give a brief overview of the Performance Optimization Productivity, or POP, project. This is the first POP webinar we've had since the service restarted in December 2018, so I thought it'd be useful just to recap a bit about what the POP project is and how it came about. So POP's the Centre of Excellence that's funded by the European Union's Horizon 2020 programme. As I said, it started on the 1st of December 2018 and it runs until the 30th of November 2021. This is actually the second phase of the project. The work I'm going to be talking about today was undertaken as part of the first phase that ran from October 2015 to March 2018. And the whole idea of the POP project is it provides free performance analysis services to people and organizations within Europe to help them understand the performance and behavior of their parallel applications. So thanks to the Horizon 2020 program funding, there's no charge to people who want to use POP. We can offer all the services that we do to people without asking for any payment, either upfront or at the end of time. And what POP does, it helps people who either write parallel code or use parallel code to understand what opportunities there are in that code to enhance the performance and then give guidance and direction on how to go about improving the performance. It's worth noting that POP is open to codes from all application areas, all scales of parallelism, all hardware platforms. We don't deal only in OpenMP codes or only in MPI codes. We accept codes that use almost any form of parallelization as being within scope of POP. And also we're not limited by the type of people who want to use it. We're not only for academic codes or only for industrial codes. We can take codes from any form of user. A brief guide, so it's a collaborative project. It has 8 partner institutions across Europe, which you can see on the slide in front of you, people in Spain, Germany, the Czech Republic, and the UK and France. And so not only do we have a great background in analyzing performance and optimizing performance of parallel codes, but some of the partners are indeed actually produce performance analysis tools that we can use on the project and that indeed people outside the project can use as well. So this is going to look as a case study at what the POP project did for Zenotech on a zCFD solver. zCFD is a density-based computational fluid dynamics solver that uses unstructured meshes to decompose the analysis domain. It's written in Python and C++ and parallelised with OpenMP and MPI, but for the purpose of this case study, we only looked at the C++ kernels that are parallelised with OpenMP. So the performance analysis that I'm going to talk about will be couched in terms of OpenMP, but the general methodology that we did this within is applicable to both OpenMP and MPI and other performance parallelisms as well. The image you can see on the right of your screen here is a visualization of the test case that we used as input for this study. It's a shock voltage case study, which was provided by Zenotech. Before we look at some of the examples of what we found and what we did on this code, I'm going to talk a little bit about the POP performance analysis methodology. So attempting to optimize the performance of parallel code can be a daunting task. It's often very difficult to know where to start. For example, you might wonder whether you should look first at how the work is divided up between threads or tasks, Or you might want to start by looking at the communication scheme that's being used, the synchronization scheme that's being used. But it may be hard to know which one of those things to go to look at first. What's the most important thing you should look at? Where should you focus your efforts to begin with in order to get the maximum benefit? And to help address this, POP has defined a methodology for the analysis of parallel codes, which provides a quantitative way of measuring the relative impact of these different factors that are inherent in parallelization. And probably the key feature of the methodology is it uses a hierarchy of metrics. So we start with a top level metric and it breaks down into sub metrics that describe different facets of performance. And this helps you to really help understand where the drivers of the performance are coming from for your particular application. And each of these metrics reflects a common cause of inefficiency in parallel programs. And the great thing of these metrics, they're numbers between 0 and 1 are efficiencies, higher numbers are better. Because of that, you can easily compare parallel performance across range of thread or process counts, across different machines or at different stages of optimization and tuning, and really use that to identify which characteristics of the code contribute to inefficiency. So as I said, metrics are numbers between 0 and 1, higher numbers are better. And as a rule of thumb for POP, we consider efficiencies less than 0.8 as being indicative that there's something further to look at under that particular metric to try and understand what's driving performance. So looking at the metrics in a little bit more detail, the headline figure, the top line figure, is global efficiency. This is a sort of one number that characterizes the performance of the program. And beneath that, the two main sub-metrics are parallel efficiency and computational efficiency. Now this slide here has the exact definitions of how we work out these metrics. I'm not going to run through them in detail. You'll get a copy of the slides afterwards to refer back to. But in general, when we talk about parallel efficiency, we're talking about what effect is the way that the code is being parallelized having on the runtime, on the performance. So it's how well is the work divided up between the computational units, how much time is lost to synchronization or other overheads, things like that. It's really the parts of the performance of the code that are determined by the efficiency of the way it's being parallelized. And the other metric, the other sub-metric, computational efficiency, it really looks at how well the individual threads or processes are performing the actual computations that they're doing. So this is looking at what's going on each thread or each process, and how efficiently is it doing the calculations that it's required to do. So that's really the two things about performance that we look at. And as you'll see on the following slides, hopefully, by breaking down performance in this way and getting a metric for each of these, it really helps guide our activities further in order to understand where the inefficiencies might be arising and also further what might actually be causing those inefficiencies as well. So this is what a set of metrics look like. This is some results from the zCFD case study. So we're looking at an OpenMP code here. We look at performance on between 1 and 12 threads, and the top line there is our global efficiency, and then below that split out a parallel efficiency and computational efficiency. And as is quite often the case across the work that we've done, we see as we increase the parallelism, as we increase the number of threads, we see the efficiencies decline. By then looking at the parallel efficiency and the computational efficiency, we can begin to gauge whereabouts the performance could be improved in order to boost the overall performance. So we can see here, for example, that parallel efficiency declines perhaps a little bit more rapidly than computational efficiency, which suggests that we might want to look first at improving the parallelization of the program before actually looking at what's going on the individual threads as part of their computation. There's also something interesting about computational efficiency, which is that whereas parallel efficiency sort of declines almost quite linearly, computational efficiency has a sudden drop on 12 threads. So between 1 and 6 threads, it declines, but it's still above 80%, above 0.8 on 6 threads. Then when we go to 12 threads, it suddenly drops down to 0.66. And that also suggests that we should perhaps be looking more closely at what's happening on the 12 thread case, particularly as to what the threads are actually doing there to try and boost the performance on that thread count. So by looking at these metrics and from what we've what our sort of understanding of the way that parallelization can happen, decide to look at three things in more detail. And these are three things that I'll investigate on the slides that follow. And these are things we looked at as part of the case study that I'm talking about. So we'll investigate more deeply how much time the code is spending in parallel code versus in serial code, because obviously we're running in parallel and multiple threads. We want to make sure that as much of that as possible is being done on, say, 12 threads rather than just on the single master thread. That's how we're going to get our performance. We'll look at the load balance of the OpenMP loops. So within the OpenMP loops, how equally is the work being shared out amongst the threads that are participating? Because if it's not being shared out equally, if one or two threads has much more work than the others, and this would explain the parallel efficiency numbers that we're seeing, and also suggest if we could rectify that, if we could balance the load better, then we would increase the overall performance of the code. We'll also look at the overhead imposed by using OpenMP. Is that unusually high as well? Is there anything we can do about that? And finally, we'll also be looking at this issue of computational efficiency, particularly on 12 threads, to understand why we see that tail off there. But looking first at parallel efficiency, so on the top line of this table here, that's the results from the previous table I showed you. But we've broken it out into those three things I listed on the previous slide. So we're looking at how much time the code spends running in parallel versus running on a single serial thread. An efficiency for load balance, so how well is the load balanced between the threads that are taking part, and then also a measure of OpenMP overhead efficiency as well. And we can see here what strikes us about this is, working from the bottom up, but OpenMP overhead efficiency, that appears quite good. It's essentially 1 or close to 1 on all thread counts, which suggests that it's not that any loss of performance isn't being caused by overheads within the OpenMP library itself. Load balance is also good. It's above our sort of 0.8 threshold, but it does still decline between 1 thread and 12 threads. So that suggests there might be something there that could be done to improve load balance and therefore improve the overall performance. But the thing that's really striking about this set of numbers, this set of metrics, is the percentage of time spent in parallel code. We notice that on 12 threads, almost a third of the runtime is spent in serial code, spending 2/3 of our time in parallel code, a third of the time we're running on a single thread. And that suggests if we could take that work that's only being done on 1 thread and also parallelize it across 12, we'd be able to get a good increase in performance from that. So you might wonder how we actually went about generating these numbers to provide this insight. For this case study, we used Intel's VTune performance analysis tool, although you could also use some of the other tools that I mentioned previously that are produced by POP partners to produce these metrics as well. I'll just demonstrate how we use VTune as part of this case study to generate these numbers. Now, if you've used VTune before, you might be aware it has a large number of different modes of analysis and screens that present results to you and things, which can be quite daunting if it's sort of the first time you've used it. What we found on this case study was we only needed to use one of the analysis types in order to generate all the metrics that we used to understand the performance of zCFD. In the version of VTune that we used, it was the advanced hotspots analysis. You can see in the top left of the screenshot on the screen now, in bold, it says advanced hotspots. I think this is VTune 2017 or VTune 2018. Unfortunately, if you go and download the latest version of VTune 2019 from the Intel website today, I believe that advanced hotspots has been deprecated, but the one they have in there now, called HPC Performance Characterization Analysis, gives you all the same figures and insights that I'm going to talk about today in terms of getting performance figures out from which you could generate POP metrics to understand the performance of the code. So all the screenshots here, I'll talk about advanced hotspots. If you're using a more recent VTune, it's probably called HPC, Performance Characterization Analysis, instead. There's a number of tabs. You can see analysis target, analysis type, collection, etc. We're looking here at the bottom up tab. So this is one grouping of results that that VTune will give, I think, for all analysis types. So we're looking at the bottom up view. It's, as I said, it's an advanced hotspots analysis, and then there's a number of different viewpoints on this analysis. Here we're looking at the HPC performance characterization viewpoint of the advanced hotspots analysis, and from this viewpoint we can get the figures to generate all the metrics in the table I showed previously about percentage of parallel code, load balance, and OpenMP overhead efficiency as well. Just one final note here, there's also another way you can look at the code. You can also group it in different ways. We're grouping here by OpenMP region. So we're looking at the different OpenMP regions of the code and just getting the performance data for each of those. So the first performance metric we talked about was the percentage of time spent in parallel code, and we can get that from this column here. So this lists the elapsed time that the code spends in different OpenMP regions and in serial code, and from that we have the first row is the time in serial code, and then we have a total runtime across the whole column, so we can calculate the percentage of the first line to all the others, and that's where we get for the 12 thread case that I talked about before, this 66% of time spent in parallel code. So that's I think quite a straightforward way of getting something very powerful straight away. Exactly how much time is my code spending running in parallel, and is there anything I need to do there to boost that? Sorry, excuse me. The next column I draw your attention to is this OpenMP imbalance column, and this is from where we get the OpenMP load balance metric that was in the previous table. What this column presents here in VTune is the amount of time VTune estimates you could save on a particular loop if that loop were to have perfect load balance. So if all the threads were to do exactly the same amount of work, then VTune estimates you could reduce the runtime of that loop by the number in this column. So we can express this as a percentage saving of the runtime, because in the elapsed time column I talked about, we know the time spent in the loop, and then this is the saving that VTune estimates we could get if we balanced the runtime of that loop, and therefore we can calculate a ratio of one to the other. And from these results, one thing we can see is that this loop on the third line down here, it's one of the longest duration loops in the program, about 0.8 seconds on this particular run I'm showing results for, but the imbalance is quite high. So VTune estimates that if we were to balance the work in this loop perfectly, we could save about 0.4 seconds of runtime on that loop from doing that. So it's a long run. It's one of our longest running loops. It's 0.8 seconds, and there's a potential to reduce that by about half, about 0.4 seconds, if we were to balance it properly. So this is us getting some more information from VTune, not just an overall metric of how much imbalance there might be present, but also a specific example of where we could look in the code to find concrete savings for runtime by addressing load balance issues. And I'll return to this later in the talk, a bit more about what this actually meant in the case study we looked at. The final column on this screenshot I draw your attention to is this one here, which is the overhead time column. So this is VTune reporting how much time is being spent in OpenMP overhead such as thread creation and synchronization. And we can see here, as indeed as the metric showed, that this is very low. It barely registers at all. So this would be something we probably wouldn't need to look at any further, because any potential savings from any issues arising here are so small. So that's introduction to the parallel efficiency side of things. If you remember back to the metrics we talked about before, there was a second one, which was computational efficiency. So I've reproduced here the top line, the computational efficiency line from the first table I showed you. including this thing at 12 threads where we see the efficiency quite sharply drop off from what it was on the previous thread counts. And just as we broke parallel efficiency down into some sub-metrics to try and further understand what was driving the performance we saw, we can do the same thing with computational efficiency. And here again, we've broken it down into 3 separate sub-efficiencies. The first of these is IPC efficiency. So IPC is instructions per cycle. It's a measure of the rate at which the processor is doing work. So how many instructions are retired, how many things does it do per clock cycle. Instructions efficiency is looking at the total number of instructions retired across the whole execution of the program. So it's a count on how many instructions are being executed. For this particular case study, we were strong scaling the input data, so we were keeping the input data the same and then just increasing the number of threads. So we would expect to see the total number of instructions executed remain the same across all thread counts. And that indeed is what we see here. The final efficiency, the CPU frequency efficiency, is looking at how the clock speed of the machines that are being used in this computation, how their clock speed changes as we increase the number of threads. And whereas IPC efficiency and instructions efficiency were good, indeed instruction efficiency was 1 across, what we noticed for CPU frequency efficiency is that it stays high for 1, 2, and 6 threads and then declines at 12 threads. And so it looks like this drop in performance we saw on 12 threads in the computational efficiency was almost entirely due to the CPU frequency decreasing sharply on 12 threads. So again, we could go and look in more detail about what might be causing that and what we could do about it as part of the performance optimization that follows generating these metrics. Again, I'll just talk very briefly about how we got these numbers out of VTune. So for the first 2 metrics, for the IPC metric and the instructions metric, we can look again at the advanced hotspots analysis. In this case, we're looking at the hardware events viewpoint. This is just a report from the performance counters on the CPU of raw figures of the number of clock cycles taken and the number of instructions retired. So here we're looking at the hardware events viewpoint, whereas before we were looking at the HPC viewpoint. Again, we're grouping here our results slightly differently to before. We're grouping by module rather than by OpenMP region. So we're looking at essentially the libraries and the sources of the code that we're actually executing here. And I'll highlight two columns of results in particular. This is the first column I've highlighted here is the number of clock ticks spent in each module of the code. From this, combined with the second column, which is the number of instructions retired, the number of instructions executed in each of those code blocks, we can compute obviously the raw instruction counter metric and then also the IPC. So IPC is instructions per cycle. We have a count of instructions, we have a count of cycles here, which gives us that we can calculate IPC and then also then calculate a metric for that IPC figure. Just leaves one final source of information. This, I said, the CPU frequency actually looked to be the thing that was causing the performance we'd observed at 12 threads. A different tab this time, but on the summary tab, which is present for all analysis types, there's one line which presents the CPU frequency ratio. This is reporting how high above or below its base frequency the CPU is actually running at. So these results here on screen now are for a single thread, and we can see it has a CPU frequency ratio of 1.236. So it's running about 1.2 times above its nominal base frequency. If we look at the same screen for 12 threads, we'll see the CPU frequency ratio there has dropped to 0.9. So it's actually running slower than its base frequency, and obviously much slower than it was on one thread. And that was where we generated a number that said that the CPU frequency drop was occurring. So based on these results, we could really conclude 3 things when we looked at zCFD. And these are 3 things that we fed back to Zenotech as things that could be addressed to boost the performance of the code. So we noted that there was a surprisingly large amount of time was spent executing on a single thread rather than on the multiple parallel threads. We saw one long duration OpenMP loop was suffering from a high level of imbalance. So if we could address that load imbalance, we could get some more performance. And finally, CPU frequency when the code was run on 12 threads was much lower than it was on other thread counts. And this was having an effect on the performance, on the actual time taken to run the code. So I said we fed this back to Zenotech, and they addressed these three things. I'll just briefly highlight what was done for each of these. So for parallelizing these serial portions of the code, what we found was that actually looking at the source code, the correct OpenMP pragmas were actually there in the code. So in the source code, more of it was parallelized than we were actually seeing. But what was happening when we looked at the compiler reports was that it found one region of code just too complex to analyze, and it wasn't applying any optimizations or OpenMP pragmas within that block of code. So although the code contained the instructions to say parallelize these loops, the compiler wasn't actually applying them. Possible this was a compiler bug or something. But the actual fix that was followed here was to remove an inline keyword, and this made the region of code smaller and easier for the compiler to parse and optimize, and that re-enabled the OpenMP pragmas that were in there but weren't previously being applied. The second thing, improving the load balance. From the VTune output, we could identify exactly which loop was suffering from this large level of imbalance, and Zenotech could then look at that in more detail to determine why this was. And what was actually happening here was that contained in this loop, in the loop body, were calls to the POW functions. This is computing a number to another power. And for certain iterations, these calls were taking an extremely long time because they were hitting a slow code path in POW, arising when both the base and the exponent that were being passed in as arguments to this function were close to 1. This is actually, I think, related to the far field boundary conditions in the actual CFD problem, but it was observable as a time spent in a function being called within inside this loop. And the way to resolve that, I mean, this POW was provided by the maths library. The way to resolve that, because we couldn't optimize the POW function itself, was to get away from this slow code path. So by transforming the base away from 1, raising it to power by calling POW and then undoing the scaling, well, that's slightly more mathematical work to do. It took POW away from this slow code path, and that boosted the performance of those iterations of the loop where this was previously occurring, and so improved the load balance of the loop overall, because suddenly the iterations that were taking a very long time previously were now much faster. It was also found that switching the OpenMP loop scheduling to dynamic also improved. So previously it was static everywhere. By switching to dynamic, that also improves the load balance as well. And the final thing that was done was to change some of the settings on the execution environment itself, so on the cluster of machines that this was running on. As I said originally, although we're looking at the OpenMP side of this code, it's part of a bigger framework that uses MPI as well. So this was being run on a cluster with the Slurm job manager on it. And by default, there's something called the CPU frequency governor was sent to on demand. And what this meant was when all the cores in the machine, 12 in this case, were being used with threads, this CPU frequency governor set to on demand was actually dialing down the frequency of the CPU, presumably for power draw or heat dissipation reasons. So it found by changing that CPU frequency governor from the default to performance, this actually boosted the performance of the threads when running on 12 threads. And what we did to show this, we actually, when these changes were made, we reprofiled the code and recomputed the metrics. So top table here that's grayed out but hopefully still visible are the metrics from the initial run of the code that I talked about at the beginning of the presentation. And at the bottom in darker are the metrics for the code after those changes I've just talked about in the preceding 3 slides have been made. And you can see the efficiencies are very much higher. So we've boosted both the parallel efficiency by increasing the amount of parallelism that's actually happening in the code, and also the computational efficiency, particularly on 12 threads, by changing the CPU frequency governor. So those metrics have shown an improvement. What we can also show, and perhaps more useful to end users, is the effect this had on the overall runtime of the code. So when we're looking at just the time it took to run the test case, for the test case we were given, on 12 threads it ran about 1.65 times faster with the modified code compared to the old code. That's obviously a nice performance improvement. Even more encouragingly, looking at another test case that was 100 times larger, we found that the modified code ran 3 times faster on 12 threads than the original code. So that's, I think, quite a nice performance increase to be able to talk about. So that's really the end of the case study. Just some general comments I'd like to make about the work we did and perhaps its applicability in more general. So hopefully I've shown that these POP metrics help you to break down the performance of the code and understand exactly where in it we could look to generate more performance if necessary, which bits are perhaps holding the code back a bit that we could improve and therefore boost the performance of the code overall. And I've shown how with VTune we can generate these metrics, but in more general, the use of performance analysis tools. So I've couched this in terms of VTune, but there are other ones out there, including the open source codes that our partners produce, like X3 or Scholastica, and these provide really good insights into application behavior. And I think the final takeaway from this case study is that performance optimization doesn't necessarily mean getting in there and having to rewrite, large swathes of your code from the ground up in order to get performance benefits. In this case, we were able to get a very good performance increase of 3 times by some relatively minor changes to the code. So, just changing the performance governor of the execution environment and ensuring that parallelization was happening everywhere we wanted it to be, gave us a 3 times speed increase. And it was thanks to using the metrics and the performance analysis tools that we could get such good results for comparatively small amounts of effort compared to taking away the code and rewriting it from the ground up. So I shall leave you with this slide. If you'd like to know more about the POP project, other examples of the work we've done, some more about the metrics and things, I direct you to this web page here. There's also an email address on there if you have any further questions about either this work or POP in general. I direct you to mail pop@bsc.es. And finally, POP has a Twitter page. So if you want to keep up to date with our latest news, I encourage you to follow POP at POPHPC on Twitter and keep up with what's going on. So thank you very much for your time. I see we've got some questions already, which is great. So I'll just dive straight into those for about another 5 minutes or so. So somebody asks, how necessary is it to tune a CFD code that you have to know CFD? Well, hopefully what I've demonstrated here is that I don't think you necessarily need to know, in general, the ins and outs of the scientific method that the code is implementing in order to be able to tune it, because of the metrics and because of the performance analysis tools that we use. As I say, it isn't helpful, but hopefully we can make a case that you don't have to be, for example, a CFD engineer to tune a CFD code, because the tools and the metrics are presented in a I guess an agnostic way for the underlying science. So I hope that answers that question. Somebody else asks, how do we ensure the metrics captured the section of code you're interested in? That's a good one. So obviously we can analyze the entire execution of the code, but only a portion of that will actually be the computational heart of it. There'll be a bunch of setup things you're not interested in, a bunch of teardown things you're not interested in. The nice thing about VTune, and indeed other tools as well, X-Ray, Scholastica as well, is that they all have APIs you can use to turn on and off collection programmatically. So you can enclose just the bits of code you're interested in with instructions to say turn on collection of performance results when you enter this bit and turn off when you leave, and that way you just get the bits that you want to look at. Yeah, another question here. So I think referring back to the slide, the final set of metrics I showed, global efficiency is only 0.56. Can it be improved further? Yeah, very much so. So this case study did an initial performance analysis of the code, proposed some fixes. These were implemented. We reanalyzed it, recomputed the metrics, and showed the performance gain. But you could absolutely use that second set of metrics as to repeat the process again and go back in and try to find more scope for performance improvement that way. So it's sort of it could be an iterative or a cyclical process where you generate the metrics, use that to get insight on where to fix, do the fixes, regenerate the metrics, and then go back and use that as the input again. So yes, very much so. It's not sort of a one shot thing. You can keep going and keep going. Somebody asks about getting the slides and if you have any publications done. Certainly, so as I understand it, you'll get sent a copy of these slides afterwards via email for yourself. I think this goes up on YouTube as well if you want to rewatch this again. And then on the POP website that's hopefully on screen for you right now, there are a lot more documents describing the metrics in a lot more detail and examples of how to compute them with various analysis tools. A couple of people are asking about the hardware configuration. The way we did this was Zenotech actually ran the performance tools themselves and passed us the results. So they used their in-house resources, which the POP project never actually had access to. So I'm afraid I don't actually know what the hardware configuration was that they used in this case. But this shows actually you don't necessarily need access to the source code in order to be able to propose meaningful performance improvements. Thanks to these tools, you can gain insight that way and feed it back to the developers that way. So unfortunately, I'm afraid I don't know the answer to that one. But it was just a standard. It was some form of Linux cluster that they ran on, as much as I know, I'm afraid. Somebody asked why we use VTune. I mean, that's a good question. There's obviously a whole variety of tools we could use. The reason we use VTune was that the authors of the code, Zenotech, were the people who are doing the performance analysis runs, and they had VTune installed already, and it was something they were familiar with. So although POP doesn't mind which tool we use, in this case we use VTune because that's what the customer was familiar with, but we can indeed use the VI HPS tools or the Barcelona tools as well. A lot of it depends on what the customer has installed, if they want to do the runs themselves, and what analysis the people doing the analysis are most comfortable with. So unfortunately, there's not really time to do a comparison of the tools in a lot of detail in this webinar. That might be something you can look at later in a different webinar. But those metrics I've talked about can be generated from a whole variety of tools, not limited purely to VTune. Well, again, I'm afraid that's all we have time for, but thank you very much for your attention and all the questions. And hopefully we'll see you again on another POP webinar in the future. Thank you very much.